Have you ever looked out of an airplane window while the aircraft was landing? As the plane approaches the runway, the pilot carefully controls its speed, angle, and direction to ensure a safe touchdown. Surprisingly, the same mathematical ideas are needed when landing a spacecraft on the moon. My interest in this topic began with Spaceflight Simulator, a game I often played after school. At first, it was simply a game about rockets and space exploration. However, as I attempted lunar landings, I noticed that every successful landing depended on mathematics. This inspired me to use Spaceflight Simulator's realistic mode as a model to investigate how controlling horizontal and vertical motion affects the lunar landings. Hello, esteemed members of the WMI Evaluation Committee. My name is Nathaniel Ezekiel C. Toledano, and I am a fifth grade student from the Philippines. Welcome to my presentation for the MMC competition, titled From Everyday Motion to Moon Landing, Exploring Mathematics Through Simulation. In this investigation, I explore how mathematics helps control motion during a moon landing and how these same principles can be observed during an airplane landing. During an airplane landing, the aircraft moves forward while gradually descending. A lunar landing experiences the same situation as an airplane landing. A safe landing is a delicate balancing act between two separate velocity vectors moving in different directions, your horizontal velocity and your vertical velocity. If the two speeds do not balance out perfectly, the spacecraft will capsize on touchdown. Math is the invisible tool that calculates this safety window. If a rocket points perfectly straight down, the engines will only slow down its fall, leaving the sideways drift completely untouched. To kill the dangerous sideways momentum, the pilot must tilt the rocket backward. By tilting the engine's fire against the direction of the flight path, the rocket can push against both the fall and the drift at the exact same time. It therefore tells us that the angle of the rocket dictates the direction of its engine power. Even after touching the runway, an airplane continues moving forward because of momentum. Similarly, a spacecraft continued moving sideways if horizontal velocity is not reduced. This leftover motion can cause the spacecraft to miss its intended landing area. To find the exact landing approach angle, I took the horizontal velocity and the vertical velocity and drew them as a right angled triangle. I used a protractor in measuring the landing angle. By dividing the sideways speed, we get a drift ratio. In space science, when the ratio is small, it matches the angles in radians. We can then convert it to degrees to see our exact physical tilt relative to the ground. Calculating the landing isn't enough. We must calculate our total combined crash, or landing speed, also known as the total structural kinetic impact using the Pythagorean theorem. This formula tells us the true speed at which the spacecraft hits the lunar terrain. The low impact tolerance of 5 meters per second will cause high speed tests to fail and explode. The math machine never changes, but as I discovered in my flight simulation experiments, changing the environmental input variables changes everything. Given the data below, I discovered that if your downward speed is bigger than your forward speed, your landing angle becomes super steep, like a scary roller coaster drop. In test 1, we almost crashed because we are dropping. But by test 3 and 4, we adjusted our speed so that our forward motion was 4 times faster than our downward motion. This gave us a gentle 14-degree angle and a perfect, soft, safe touchdown. At 3.7 meters high, our landing angle was 53 degrees instead of a perfect 90-degree angle, but we still landed perfectly. Why? Because our total combined speed was only zero point 0.5 meters per second, meaning that structural impact was perfectly safe. This proved to us that while a 90-degree angle is a target, staying super slow is the ultimate secret to surviving a landing on the moon. Our moonlander travels an actual horizontal distance of 2.78 meters over a total airtime of 9.25 seconds. Next, we look at our crash data below. We discovered that even if you slow down your downward drop, like in test 5, where it was only zero point 0.2 meters per second, you will still explode if your horizontal speed is too high. Our landers were screaming across the moon at 100 meters per second, creating a very flat 4-degree and 5-degree angles. This proved to us that you must burn your engines backward to stop the forward slide before you get close to the ground. Every single one resulted in an explosion. This math proves that every vector direction contributes to the final impact energy. During a normal flight on Earth, the pilot inputs parameters to maintain a massive horizontal velocity to generate vital wing lift over the runway, resulting in a flat 3-degree landing approach angle. However, my data collection inside SFS proved that copying an airplane's flight profile on the moon is a recipe for disaster, because space is a vacuum with no air for wing and no paved runways. Carrying high horizontal velocity causes the landing gear to snag on the lunar dust, tripping the vehicle into a catastrophic explosion, as seen in my early 4 and 5-degree crash tests. To survive, a moonlander must execute a backward retrograde burn to destroy all forward speed, transforming its trajectory into a vertical 90-degree straight drop where its downward velocity is carefully throttled to under 3 meters. What began as a game I played after school became an opportunity to explore mathematics through simulation. Using Spaceflight Simulator, I investigated how speed, momentum, and direction affected a lunar landing. Most importantly, I discovered that these mathematical ideas appear in everyday experiences. Every airplane landing demonstrates the careful balance of horizontal motion, vertical motion, and direction. Mathematics help us understand both extraordinary achievements, such as landing on the moon, and familiar experiences, such as going to vacation by airplane. Distinguished judges of the World Mathematics Invitational, my project proves that math is not just symbols in a textbook. It is a living, universal code. The same trigonometry that calculates a smooth airplane flight for our holiday vacations is the exact same math driving the physics engine of Spaceflight Simulator, and the very same vector logic we use to safely navigate a playground slide without scraping our knees. The rules of the universe remain constant. It is simply up to us to calculate the right balance of forward and downward speeds to safely land our dreams. Thank you very much, and I wish everyone a successful tournament.